My dear friends, welcome to Rajshekhar classes on Applied Data Science with Python. This is lecture number 405. In this lecture, we will try to understand various cases for decision trees. The first case would be imbalanced data. When you have imbalanced data, you have to balance it. You have to balance the data either using upsampling or downsampling, because imbalanced data impacts entropy. For example, 90% data is of positive class, 10% of data is of negative class. This impacts your entropy calculation, or even it also impacts mean squared error calculation, that is MSE calculation. So for imbalanced data, it is very important to balance the data and then apply decision trees. Otherwise, things will go crazy. The second thing is, what if we have large dimensionality? Second case is, what if we have large dimensionality? If you have large dimensionality, at each node in the decision tree, we have to split it. We have to evaluate each of the features. To compute information gain for each of the feature splits. The number of features is same as dimensionality of the data, which means your time complexity to train the decision tree increase dramatically, especially when you have large dimensionality. Large dimensionality of data or large number of features. So what if we have categorical features? Let's assume you have categorical feature. The recommendation is we should avoid one-hot encoding for categorical features. If you have a categorical feature f, which is one feature, if it has 10 distinct values, in one hot encoding, one feature will converted into 10 features, because in one hot encoding we create new variable for these 10 features. Therefore, dimensionality increases. As my number of dimensions increases, the time complexity to train will increase. So when you have categorical features with lots of categories or lots of levels, as it's often called, it's useful to convert them into numerical features. And how do we do it? We convert it using probability of yi equal to 1 given the feature, the feature value has some category C1. We saw this is in one of the previous lectures, especially with categorical feature with lots of levels. It's useful both for speed and for interpretability, and to avoid overfitting, to avoid data sparsity issues, it's useful to convert them into numerical features using this probabilistic conversion. Now the next thing is, what happens given similarity matrix? Decision trees cannot work. Decision trees need the features explicitly, because if I don't have the features explicitly, I cannot compute entropies. Given similarity matrix, decision trees, regular definition of decision trees cannot be made to work easily and smoothly. And what if you wanted to do multi-class classification? And what if you wanted to do multi-class classification? Of course, you always has one versus rest, but you don't have to do one versus rest in the case of decision trees. For example, let's assume, because entropy is calculated for random variable y, even if it has multiple categories y1, y2, y3, so on, yk. Entropy is not limited to two categories, not just entropy, even your Gini impurity, which is your Gini impurity, can be computed when your y takes multiple values, isn't it? And what happens at leaf node? For example, at leaf node, let's assume you have three classes. What are those? Y can take three classes. What are they? Let me assume these are the classes 1, 2, 3, isn't it? Suppose if I have 10 points of class 1, just see, 10 points of class 1, 5 points of class 2, and 3 points of class 3, isn't it? Let it be. Which is the majority is? Which one is majority? Let me say, if a query point reaches, let me assume your query point reaches this node. Your query point is here. If query point reaches here, xq reaches here, then I will say the class label. What is my class label? Class label is 1. What is the reason? Because majority of the points belong to class label 1. So doing multi-class classification is straightforward. You don't have to do one versus rest. Decision trees naturally can be extended to do multi-class classification, because entropy or Gini impurity can be computed when your capital Y takes multiple values naturally without any problem. The next thing about decision surfaces, what is this decision surface? The next thing about decision surfaces, what is the decision surface that you will get in decision tree? Decision surface you will get is non-linear, and decision surface you will get are axis parallel hypercuboids or hyperspaces. Because if you have a region like this, let me say you have a region like this. If I break it up like this, let me say I break it up like this. What is this? This is hypercube. What is this? This is hypercube. This entire thing is known as hyperspace. Decision surfaces are completely non-linear. It's not just like one line like this. It is decision surfaces are just not like this, not just like this one line, isn't it? That's what it says. I can say it's not just like one line like this, isn't it? You no more learning one line. You are learning lots and lots of hyperplanes in your decision tree. One decision plane corresponding to each of the node. Just see what it says. One decision plane corresponding to each decision plane corresponding to node, isn't it? Yes, this is one. What it says, this is pi, decision plane pi. Each decision plane corresponds to a node in decision tree, isn't it? Now I can say node corresponding to plane. No, every node corresponding to plane, isn't it? Each of these nodes has a plane corresponding to it. Just see, here you have a node. Let me say for that corresponding plane will be there, which are each of the nodes. This is a node. This is a node. This is a node. Each of the nodes has a plane corresponding to it. which is these planes are axis parallel planes. So what you get basically an axis parallel tessellation of your space. That's what your decision surfaces of decision trees looks like. Just go through these points. If you have any difficulty, please keep a comment. Thank you very much.